So what is m of omega? M of omega would be the Fourier transform of this times the first term, which is k, f of omega. And what does the t minus t naught contribute to in the Fourier space? Not h, but a shift, right? A shift. It contributes to that shift. Okay? And then the second term would be just, what does it do if you multiply this thing by this thing over here? It will just translate or shift the Fourier transform by that amount. Okay, by that amount over here. But then you can shift it first before you add the phase, so it will be 1/4 k f of omega minus 2 omega c, okay, e to the minus j omega t naught. This is what it does to that thing over there. Okay, let me see if I do it correctly. So it shifted in this direction. Okay, I think the direction is correct. And then the second term would contribute to something like 1/4 k f of omega plus 2 omega c times the phase shift due to the delay. The phase shift due to the delay is just e to the minus j omega t naught. Okay. There's a 1/2 here, right? There's a 1/2 there. Okay. Okay, so can you understand how I write the last line over here?
Yeah.
Okay.
It's easy.
It's easy, right?
Gibbles like
Simple piece of cake. Duck soup. Very easy. Okay? Have you heard of the term duck soup?
No.
No? Maybe it's a very old term. You're too young for that.
I know what duck soup is. Soup. Yeah. Soup made out of duck?
I don't know. But, so, let's see. There are 3 terms over there. Then the spectrum will look something like this. You have one that is centered around the original bandwidth, but only with the phase modulation. Okay, so this m of omega will look something like this. And then you have another one, which is smaller in size, over here. Okay, so the spectrum of the incoming signal looks something like that. One clever thing that you can do to pick up the original signal from this spectrum, pass this to a low-pass filter. Very clever. Okay, very clever. Pass this to a low-pass filter, and the low-pass filter will just pick up this term, and then you Fourier transform this term back to the time domain, and you will hear the nice voice signal from your mom or your dad. Okay?
Maybe you're yelling at you.
Maybe you don't want to hear that.
Use a high pass filter.
Use a high pass filter. So I think this is all you need to know for the demodulation part.
Oh, that was going to be hard.
And the thing about this coherent detection is that demodulation. Okay, coherent demod is that this time delay has to be exactly matched to the time delay of the signal. And this time delay cannot be that certain because as you send the signal from Chicago to here, it hops through a number of places, hops through a number of equipment. And that delay is actually not known. So you have to have very clever electronics to latch onto the delay, or to lock onto the delay. And then lock onto that signal, okay, it's called signal locking. Then you can do this demodulation. So coherent demodulation requires quite sophisticated electronic design. There is a cheaper way of doing demodulation, which some of you might have heard of before. What is that? Any one of you play around with crystal radio diodes and the kind of thing? Rectifier circuits?
Yeah, when I'm bored.
What is that? When you're 1 year old?
No, when we're bored.
Well, what's
what we do?
When you're bored, okay. So the idea is that you have a voice signal coming in. Okay, you add a constant to it. You add the platform to the voice signal so that it never goes through 0. Okay, and then you use this voice signal with a platform, use it to modulate and the carrier. Okay, if you do modulation with this signal, then the carrier will look something like this. Okay, so the transmitter thing will look something like that. Okay, but now if you get this signal, if you pass that through a diode, the diode is something that just looks like that. You might have learned about this diode in your other course. What does it do?
It's gonna cut off everything.
It is a rectifier. It only lets current flow in one direction but not the other direction. So as this AC signal is coming in, you will just cut off all this. So after it goes through the diode, so what you have is just the upper half. The upper half of the signal. This is rectified. Okay, so this rectified signal can be thought of as a high frequency signal plus the low frequency signal sitting on top of it. Okay, and then you just pass this through a low pass filter. Okay, let's just go to the low pass filter. The low pass filter will remove the highly oscillating part. Okay, and then it will give you back the signal, because it removes all the high frequency components, and then you can just remove the DC component, the alpha component, and then you can get your voice signal back.
They have implemented this.
What is that?
They have implemented this in your lab.
Oh, you actually did this in your lab?
Yeah.
And
Lab 1.
You're not aware of that?
Not aware of anything.
Okay.
We just followed the instructions.
You just follow instruction and did, right?
We just
Monkey see,
nodded our
monkey
heads
do.
and
We were
agreed.
so confused the first time.
Okay.
All
This
of
is
that.
what happened to you. Lab work. Okay,
nice
it's
to know.
doing all this kind of
They should put lab work after.